Watch sizing is a complex balancing act between multiple dimensions. I've always wished there was a better way to get the size of a watch besides the diameter, which can be quite inaccurate because you're not always going to be able to try it on in person. So over the last few weeks, using a lot of math and geometry, I developed an equation that calculates the actual size of a watch by putting numbers to the effect dimensions actually have when it's on the wrist. So how does this equation work? In principle, it's a way of calculating the perceived diameter of a watch using the listed diameter, lug-to-lug, and thickness measurements. If you want to try it out, I've included a link to a Google Sheets spreadsheet in the description of this video that does all the calculations for you. Just enter in a watch's dimensions, and it'll tell you its estimated perceived diameter. Optionally, you can enter your wrist measurements, and it'll even calculate how the watch wears for you, your ideal size, and more. But I'll get to that part later. As for the equation itself, it's essentially two correction terms added to the watch's actual diameter. The first is the lug correction term, or L-core. This estimates how much of an effect the lug-to-lug length has on the sizing. The other is the thickness correction, or T-core. This estimates the effect the given thickness has on the sizing. This term is significantly more complicated, mostly because it's actually two equations, a positive and a negative T-core. Going back to the spreadsheet, if I enter in the dimensions for, say, the Tudor Black Bay 58, you can see that it actually wears closer to a 40mm watch than a 39mm. Entering in Seiko's SKX case measurements, on the other hand, shows that the SKX actually wears around a millimeter smaller. Now that you've seen how it works, I want to spend the remainder of the video explaining the expanded form of this equation, how I derived it, and my method for determining someone's perfect watch size. While the spreadsheet is neat, I think the journey of how I got to it is the real meat of this discussion. All mathematical proofs and derivations begin with a set of accepted axioms that form the base from which the reasoning is constructed. To create this sizing equation, I based all of my reasonings on three key and well-accepted axioms. 1. Most watches follow a relatively standard format of shape and sizing. Nearly all circular watches are a cylindrical head with a diameter, thickness, and attached lugs that form a lug-to-lug distance. Geometries will vary, but this is almost always the case. 2. Perceived size is dependent on the projected area of the watch. A watch is a three-dimensional object. When viewed from any angle but directly above or directly to the side, the silhouette of the watch is dependent on both its span across the wrist as well as its thickness. 3. Holding all others constant, larger dimensions wear bigger. Take two identical watches with the same thickness and lug-to-lug, but with different diameters. The watch with the larger diameter will wear larger. The same goes for any other dimension if all other dimensions are held constant. To put it into mathematical terms, the function of each dimension compared to its wearing size is continuous and constantly increasing. These three statements will form the basis of the math needed to calculate the perceived size of a watch, and must hold true for our final equation. So, getting back to our simplified equation, as I said, we have the lug correcting term and a thickness correcting term. Both of these follow a similar structure, an expected contribution or difference value multiplied by an average correcting value. The idea for each is to calculate the expected contribution to the diameter based on the dimensions, and then to correct that value based on what we see from averages of a large dataset of watches. It sounds complex, but it'll make more sense when we get into it. Let's start with L-core. For the lugs, the expected contribution is simple. We want the typical diameter a watch would be that has our lug length, that we'll call G expected, subtracted by the actual diameter. This gives us the difference between what diameter our watch should be and what it is. To find D expected, I compiled a list of the dimensions of hundreds of popular watches and calculated the averages of the relations between the different dimensions. Through this, I found that a watch of average lug length for its diameter will have a diameter that is roughly 85% of its lug-to-lug measurement. Therefore, we say the expected diameter of a watch according to its lug length is 0.85 times that lug length. We now have the expected contribution. Our watch isn't the expected diameter though, so we can't add the full value to our actual diameter. We need to correct this with an estimate on how our watch's area compares to one that has that expected diameter. Before we get to that, real quick, if this sort of scientific and analytical style speaks to you more than the typical watch channel, consider subscribing. This type of educational watch content is what sets my content apart from others in the space, and joining the channel lets me know what topics resonate more with my viewers and what I should be making more of. Thanks. Let's define the shape of a watch's span across the wrist simply as a rectangle with width equal to the diameter and length of our lug-to-lug. We need three areas: the expected area due to the actual lug length, the expected area due to the actual diameter, and the actual area due to the true lug length and diameter. To find where our actual diameter is in the range from minimum to maximum contribution, we calculate the ratio of the difference of the expected area from the actual area to the difference between the expected areas. If we go to our sample of dimensions and calculate this for every watch, and then find the average of all these ratios, we find that it approaches 1/2. We call this average correction ratio C bar L. It tells us that a watch's actual area sits halfway between the expected areas due to the lugs and diameter. Since the expected area due to the diameter corresponds to a contribution of 0, we know our actual contribution is 1/2 the contribution of the expected area due to the lugs. So we now have the contribution of the lugs towards the overall perceived diameter. Next, we move on to the thickness. The thickness term follows the same form as the lugs, an expected contribution term and a correction term. For the contribution term, we need to find the difference between the actual thickness and the expected thickness due to the diameter. In order to avoid double counting, let's use the new diameter resulting from L core. From my sizing analysis, I found that an average watch will have a thickness about 29.5% of its diameter in length. So T expected is 0.295 times the new diameter. The reason we aren't finding the difference of the expected diameter due to the thickness will become more apparent in a bit. For now, let's call this contribution term T diff. Next, we have the correction factor, and much like before, we calculate this from the areas of our expected thicknesses. Because of our second axiom though, we need to estimate this with what's called the projected area of the watch on the wrist. Let's define the shape of the watch head as a cylinder with diameter d and height t. The area of the watch's silhouette would then be this expression for the projected area of a cylinder, where theta is the viewing angle of the watch. We look at a watch from multiple angles though, so a good approximation for all of these would be the average projected area over the common view angles of the watch on our wrist, which would be from directly from the side, that we'll call theta equals 0, to from directly above, that we call theta equals pi over 2. The average projected area is its integral over those angles, all divided by the size of our angle range, which is just pi over 2. We end up with this expression after some reducing, since sine and cosine over this range are 1, which coincidentally is the same reason we didn't need the projected area for L core. So anyways, how is this useful? Well, just as we did before with the lug correcting term, we need to compare the areas from our actual measurements to the expected ones to see where our measurement lands in that range. To find d expected, I calculated the projected area for a diameter and thickness, and equated it to another projected area with a thickness 1 mm higher. Solving for that new d yields d expected for that diameter thickness combo. Repeating this for an array of inputs and plotting the differences between d expected and d shows a roughly linear relationship of about 0.5. This means that for every millimeter of added thickness to a watch, its visual area corresponds to a watch with a 0.5 mm bigger diameter. This also explains why we needed the T diff from earlier and not D diff. This correction term measures diameter difference per thickness difference. The best fit of all these D expected gives us C bar T, which corresponds to this expression, and gives us the full form of T core in the positives. Added thickness always makes a watch larger, essentially linearly, but the inverse isn't exactly true. There are diminishing returns to a watch getting thinner. After a point, it doesn't matter how thin the watch is made, the span and perceived area of the lugs and diameter can't be eliminated. Because of this, I believe that for negative T-core values, the T-diff needs to be adjusted to an exponential curve instead of a linear one. I did this by following this form, where T-diff is now the power of E over a constant. This models the diminishing returns of lowering thickness. As for the constant A involved in this equation, I played with these until they gave values that looked roughly correct in relation to a watch's dimensions. This is perhaps the only aspect of the entire equation I don't have a physical explanation for, but I'm sure one could be made. Regardless, we implement this negative T-core in the form of a piecewise function. If we first calculate T-core and it's positive, meaning the thickness is making the watch look bigger, we keep T-diff the same. If T-core is negative though, we then calculate it again using the exponential T-diff and use that resultant T-core as our final contribution. And thus, we have our final equation. Perceived size is equal to the diameter plus L core and T core. This approximates the size of our watch to that of an average watch of the resultant diameter. Earlier, I mentioned that the spreadsheet estimates how a watch will wear on your wrist as well. So, how does it do this? The calculation is actually rather simple, and it's based around a simple principle. A watch with lugs that extend beyond the edges of your wrist is likely to be too large for you. We first need to measure our maximum wrist width. This can be done with calipers or with a pen and paper, marking the maximum distance from above. Either way, it's very important that the measurement is in the supinated wrist position, meaning with your palm facing you. This is because when rotating or pronating your wrist, the bones in your arm twist over top of each other. This physically lowers the measurement, and is one reason why watches look bigger when checking the time versus in the mirror. I found that around 88 to 90% of this supinated measurement corresponds to a typical maximum lug-to-lug a person can pull off on their wrist. We then multiply this maximum lug-to-lug by 0.85 to get our expected average maximum diameter. Dividing the perceived diameter by this maximum diameter then gives a percentage of maximum size. Different values of this will correspond to various wearing sizes for your wrist, from vintage sizing to ideal to probably too large. I think I did a fairly decent job adjusting these ranges, but of course, sizing is in large part preferential, so you may feel differently. At the very least, I found that they work quite accurately for my wife and I's wrist dimensions. Next, we have your wrist height, which influences the thickness to wrist height ratio. Just as it sounds, we divide the watch's thickness by our wrist height or thickness to get another percentage. To measure wrist height, complete the same process as before, but rotated 90 degrees. Again, thickness preference is exactly that, a preference, so these are subjective. But based on my testing and research, a percentage of about 29% seems to be a neutral thickness on the wrist. Every 3-ish% corresponds to a different style, from ultra thin all the way to watches that are likely too thick. Thinner wrist will be most affected by a watch's thickness, while thicker ones not so much, which is reflected in this ratio. I'm a firm believer that listed diameter doesn't tell the whole story of how a watch wears, and I think today's obscure reference is a great and incredibly interesting example of that. That's because the JLC Memovox E877, dubbed the Snowdrop, is a completely circular watch without any traditional lugs. Released in the 1970s, the Snowdrop maintains a funky design somewhat typical of the era, with a rounded case, domed crystal, hidden spring bars, and recessed dual crowns, because of course, this is a Memovox alarm as well. It measures in at either 43 or 42.5mm in diameter, but it wears much smaller. Putting the dimensions into my calculator, it wears about 2mm smaller than its listed diameter, and probably more like a modern smartwatch than a traditional mechanical one. This model came in various different styles, from black, striped, and silver dials, various colored hands, to 2 different bracelet styles as well, both of which are fairly unique in design. All of them share the center disc and arrow design though, which indicates the setting of the alarm. As far as acquiring one goes, the limiting factor is definitely how rare they are. It's reported that only about 2,000 were ever made, so finding one is quite unlikely. Regardless, designs like this are still around in modern watchmaking and continue to show the diameter is a pretty meaningless measure on its own. And really, no matter how many dimensions you have, it's still difficult to tell the true size of a watch from just numbers. I'd like to think my work here is accurate, but even complex equations like mine have their limitations. For example, the perceived size equation only finds the relative size of the silhouette of circular styled watches. It doesn't take into account the dial to bezel ratio, colors, complex geometries, square watches, and more. It could certainly be improved, but even if it was, it's only an approximation at the end of the day, and sizing is largely subjective in the first place. At the very least, I had fun making it, and thought the process was productive in understanding watch sizing a bit better. Hopefully, some of you may have found it interesting or helpful, particularly for watches you don't have the ability to try on in person first, like with microbrands, vintage pieces, or especially rare references. And if you're interested in a deeper dive into every aspect that goes into watch sizing, make sure to check out my video on that here. I go over the intricacies of sizing beyond just dimensions and touch on some aspects you probably never considered before. But as always, thank you for taking the time to watch.